All right, let's dive into one of the most ingenious little tricks in the world of chemistry. It's called polarography, and it's an incredible method for seeing what's totally invisible in a solution, all with the help of a single, tiny falling drop. So, think about this for a second. It sounds like a riddle, right? How on earth can one single drop of mercury tell you the exact amount of a pollutant, say a heavy metal, that's hiding in a glass of water? It seems kind of impossible, but that's exactly the question we're going to answer today. So, how do we solve this riddle? Well, the answer is a brilliant technique called polarography. It's been around since the 20th century, and trust me, the way it works is just so cool. At its heart, what is polarography, really? You can think of it like this. You're basically using electricity to interrogate a chemical solution. You apply a little changing voltage, you carefully listen to the electrical current that comes back, and just by doing that, you can get the solution to spill all its secrets, what's inside and exactly how much. Okay, I know that still sounds a bit abstract, so let's pull back the curtain and see how this thing actually works, step by step. And you'll see the real genius here is just how simple the whole setup is. First up, you take this special little microelectrode and you pop it into your liquid sample. Easy enough, right? Then comes the fun part. We start applying a voltage, but we slowly ramp it up, kind of like turning a dimmer switch on a light. As that voltage climbs, something amazing happens. Different chemicals in the solution start to react, but each one has its own magic number, a specific voltage where it wakes up and does its thing. That reaction creates a tiny little electric current, and that's the signal we've been waiting for. All we have to do then is measure it and plot it out. And what you get is this beautiful graph called a polarogram. You can think of it like a chemical fingerprint. Each substance creates its own unique S-shaped wave. Now, where that wave appears tells you what the substance is, but the real secret, the part that tells you how much is there, is the height of that wave. The taller the wave, the more of that chemical is in your sample. It's a beautifully direct relationship. Now, this all sounds great in theory, but there's a secret ingredient that makes the whole thing possible. It's the absolute game changer, the secret weapon that makes polarography so incredibly accurate and reliable. And it's all about that dropping mercury electrode. So you're probably thinking, oh wait, mercury? A falling drop? Why not just stick a regular metal rod in there and call it a day? And that is a fantastic question, because the answer is pure genius. So here's the deal with regular, solid electrodes. Imagine trying to see through a window, but every time you look, the window gets a little bit dirtier. Eventually, it's so covered in gunk that you can't see anything clearly. That's electrode poisoning, chemical buildup that ruins your readings. But the dropping mercury electrode has the most elegant solution imaginable. Each drop provides a perfectly clean surface, and just as it starts to get contaminated, it falls away and a brand new pristine drop takes its place. It's like having a self-cleaning sensor that resets itself every few seconds. No more poisoning, just perfectly clean data every single time. And it turns out mercury is pretty much the perfect candidate for this job. For starters, it can operate over a wide electrical range, so it can detect a whole bunch of different substances. We already know its surface is perfectly renewable, which is amazing, but here's the kicker. It's fantastic at absorbing the very metal ions we're often looking for, like those nasty pollutants. That's the process that generates the current we need to measure in the first place. Okay, so we've got this super clean signal from our magic mercury drop, but how do we translate that electrical current into a precise concentration? We need a key, a sort of decoder ring, to translate the information. And in chemistry, that key is a famous formula known as the Ilkovic equation. The whole point of the Ilkovic equation is to be the bridge between the world of electricity we can measure and the world of chemistry we want to know about. It lays out a simple, rock-solid fact. There's a direct, linear relationship between the current you measure and the concentration you're looking for. The beauty of this is how simple and predictable it is. If you double the amount of a chemical in your sample, guess what? The current you measure also doubles. It's exactly proportional. It's this direct relationship that turns polarography from a cool trick into a powerful scientific tool. And here's the equation itself. Now, don't let the letters and symbols intimidate you. It's actually much simpler than it looks. On the left, ID is the current. That's the number we get from our graph. On the right, the most important piece of the puzzle is C, the concentration. That's the treasure we're hunting for. Everything else? Well, those are things we already know. They're either known properties of the chemical, or they're settings we control on the instrument itself, like the size of the mercury drop and how fast it falls. So, since we know everything else, solving for C is just a bit of simple math. So, this is all fascinating science, but what about the real world? I mean, why does this technique, which is almost a century old, still matter? Well, you might be surprised to learn just how widespread its applications are. In environmental science, this thing is a rock star. It's perfect for sniffing out tiny but dangerous amounts of heavy metals like zinc and cadmium in our water. Industries use it all the time for quality control. It gets used in organic chemistry and even in biochemistry to analyze what's going on in biological fluids. It's this quiet workhorse of a technique that's been proven reliable for decades. So let's just tie this all together with a bow. Polarography uses a constantly renewing mercury drop to get an unbelievably clean electrical signal. It then uses the Ilgovic's equation as a translator to turn that signal into the exact concentration of a substance. It is, from start to finish, a simple, elegant, and incredibly powerful idea. And that really leaves us with a final thought, doesn't it? This is a 20th century technique that figured out how to use electricity to literally see chemicals. In our age of hyper-advanced, complicated digital sensors, it really makes you wonder, what other huge problems could we solve not by building something more complex, but by going back to clever, beautiful first principles, like this one?